Macko, or you can call me Vlejd. And I'm here to talk to you about how you can do machine learning if you have access to a lot of GPUs, for example, from Google. I studied in Comenius University in Bratislava, where I got my master's degrees. And during school, I worked for 4 years in various machine learning projects, in various machine learning companies like Black Swan Rational and Central European AI. And I speak here today because last year I spent in New York, in Google Research New York, at a program called Google AI Residency as an AI resident. This talk will have 2 parts. In the first part, the non-machine learning one, I'm going to speak about the residency, what it is and how to get there. And in the second one, I'm going to speak about what I did during the residency, and more particularly, about the team that I joined, which is called AdaNet, and this team is working on AutoML. So we are going to talk about what AutoML is, how is it in theory, and how is it in practice. So, this is an AI resident. For a time period of 1 year during the residency, the sole purpose of the resident will be to ingest latest machine learning research and produce novel papers that are publishable on top-tier venues. Pretty much everyone can become an AI resident. And last year, there were people with various degrees from various backgrounds. There were some bachelors, masters, PhDs, or even industry professionals. These people were from computer science, machine learning, math, physics, but also from biology, medicine, and fields like music. And AI residents can have different destinies after they end the program. Some of them return back to academia and continue their PhDs or become professors at renowned universities. Some of them return in the industry and put on a hard hat and continue with the hard digging. And they either remain in Google or go to a different large company, like Facebook, for example. And some of them just go on a prolonged vacation, which is what I did. For me, personally, the AI residency was pretty much like a 1-year-long PhD program that is very well paid, and you have access to much more compute and even much more human resources that you would normally get. So for me, that sounded pretty cool. The only question is how to get there. Well, the process is fairly straightforward, even though it's not very easy at all. It starts with the applications. And you need to send your application, your CV, your referral letters, and a bit of a cover letter. And if you are lucky enough and your application is recognized amongst thousands of other ones, you proceed to the next round of phone interviews. If phone interviews go well, you are invited to the on-site interview where you spend 2 sessions on one-on-one interviews with Google research scientists that's going to ask you questions about machine learning, math, or computer science. Again, if everything goes well, the only thing remaining is to match your project preferences and your research preferences with a particular site where the residency was happening that year. And finally, you just need to survive a trip to New York and trip from New York airport to your current accommodation, which turned out to be surprisingly complicated. Well, this process is fairly straightforward and kind of standard across multiple companies, so there is not much special there. But it has some very nice quirks. Like, for example, if you are invited to the on-site, you can have a lunch with machine learning legends like Mr. Hinton, Goodfellow, or even Jeff Dean. If you don't know who's Jeff Dean, he's a guy responsible for nice tools like Google Search, MapReduce, or TensorFlow. And he's a level 11 in a corporate leveling system where the highest level is 10. Oops, what? Sorry. Yeah. In hindsight, it looks like there are some very strong indicators of people who got into the residency and people who didn't. It looks like the very important thing is to have a previous experience with Google, like, for example, have an internship there, but any form of industry experience is definitely a large plus. Surprisingly enough, it's not required to have a PhD for this program. even though if you would like to be a research scientist in a big company, the PhD is pretty much a requirement. So this program is a nice way how to do research in a big company, even though if you don't have this degree. And finally, you need a ton of luck, especially in the first stage, because the number of applications is in thousands, and only a handful of people are actually invited to the next round. For me personally, I think the thing that got me there was that I was bold enough and took a photo with Mr. Dean on the on-site interview. And this turned out to be a very good predictor of who gets in, because 2 people got the picture and 2 of them got into the residency. So, a coincidence? Probably yes, but you know, we are machine learning people. After you get to the residency, you are faced with the last question, and that is what to do there. Some people have no idea. Some people had a particular project in mind. And for those that don't know, there was a set of lightning talks where researchers proposed their ideas that they are willing to mentor. I personally ended up in a team called AdaNet, which is an AutoML team in New York, and we are going to talk about it in detail later in this presentation. As my second project, I worked on graph neural networks and machine learning for combinatorial optimization and speeding up mixed integer program solvers. But that's a topic for another talk. This one was actually quite nice because it was in collaboration with DeepMind. So, having said that, I would like to conclude the first part of this talk. That was the non-machine learning one, and we can start with some ML. So it's time to check the time. Have a bit of a refreshment, so brace yourself. Here we go. Please, first of all, show of hands. Which one of you have tried to reproduce some recent machine learning paper recently? Okay, few hands. Nice. Which one of you got the same results as the people in the paper? I don't mean like exactly the same results, but your results would lead to producing the same paper as those people did. Okay, that's quite impressive. Personally, for me, this was a huge pain in the ass to do properly. And why? Well, you need to get a lot of things right. From the obvious ones, like you need to have a correct neural network architecture. You need to use the same set of hyperparameters. You need to process your data correctly. You need to use the correct training schedule and all the training tricks that these people did. And finally, you need to have a correct version of everything. Well, some of these things are fairly well described in the paper, but then you have a set of more exotic things, like you need the same compiler flags, you need to use all the same hardware tricks, and God forbid if you are trying to reproduce it on a different hardware or in a different library, because those things usually have very surprisingly different defaults. Actually, the last time I tried to do something like that, I had to go through a set of lovely around 40 to 50 parameters, and I had to set every one of them correctly. Some of them were in paper and were kind of obvious one, like learning rate, but some of them were, let's say, more esoteric, like XLA-JF use rotated pincer emitter 2D. And the problem with current machine learning research is that most of these parameters had to be kind of set up by some expert, and they need to be set up correctly. And usually your experiments are quite sensitive to these things. So the question is, what can we do about this? Well, wise man once said that right now, machine learning solutions are comprised from machine learning expertise, data, and computation. And the question is, can we somehow get a bit rid of the machine learning expert and just replace it with more computation? And that's pretty much what AutoML would like to do. So if you would like to replace the machine learning expert, first of all you need to know what does the machine learning expert actually do. Well, they set up the data processing and try to figure out what data augmentation to use. They decide what architecture is correct for this problem and what the model should actually look like. They set up the hyperparameters, and finally they actually decide what combination of these things is the correct one to use. Luckily, it turns out that almost all of these things could be to some extent automated. Like, for example, data processing can be automated with something called AutoAugment. Architecture selection is done by a subfield of machine learning called architecture search. You can do hyperparameter tuning with things like Bayesian optimization. And finally, you can use cross-validation to decide what parameters and what combination of these things to actually use. Well, and the second thing, the architecture search, is the thing that we are going to talk further in this presentation. However, if you are a machine learning practitioner in the wild, you probably know that a lot of work that you need to do is actually with things like model debugging, diagnosis, and plumbing, and just setting up your pipelines correctly. And that thing is probably not going to be automatized anytime soon, even though there are some efforts to do that. So, how do we do architecture selection right now? Or how does the expert do does the experts do architecture selection? Let's say we would like to solve a problem like image classification. So what do? We just take a bunch of layers that we know that work well for the problem, like max pooling, convolution, and dense layer. Then we decide how much time and how much memory or resources we have and how big model we can afford to train. And we just take those layers, put them on top of each other, and fill our parameter budget with trainable parameters. And what people usually arrive at are these lovely one-tower architectures, where those blocks are just stacked on top of each other, and they have some width, which is, for example, number of convolutional kernels or number of hidden UD in the dense layer. Well, that begs the question, is this optimal? And is there a better way how to spend the parameter budget? There are two sub-questions to this one, and the first is, are we stacking the correct blocks? And aren't there some nicer and more awesome blocks that we should use? And the second question is, are we stacking those blocks in the correct way? Well, the first question, what blocks to stack, was partially addressed by a paper called Neural Architecture Search with Reinforcement Learning. Authors there employed a reinforcement learning algorithm to let it learn or predict the optimal block architecture that should be used. The algorithm predicted two types of blocks or cells, normal cell and reduction cell. Then they took these cells and again just stuck them on top of each other into a single tower architecture. And they got state-of-the-art. The second question, how to stack those blocks, was partially addressed by a paper called AdaNet, Adaptive Structural Learning of Artificial Neural Networks, where authors proposed a rigorous theory based on learning guarantees, and on top of there, they proposed an iterative algorithm that grows an ensemble with more and more complex subnetworks. This algorithm iteratively possibly proposes different subnetworks of different architectures and find out what the final ensemble or the final model should look like. This paper led to a creation of a team called AdaNet that is currently residing in Google and was currently merged with something called AutoLX, which is an AutoML team in New York. Well, and I joined this team and tried to extend some of the results proposed in the paper in our own publication called Improving Neural Architecture Search, Image Classifiers via Ensemble Learning. So let's dive into the algorithm. It starts with the three things. We have our dataset S, we have the number of iteration I, and we have a generator G. We start with an empty ensemble or with nothing. Then we will run in iterations. In each iteration, we propose a set of candidates. We train each of those candidates independently, here. Then we try to add them to the ensemble and see which one of these which one of these candidates improves the performance of the ensemble the most. Then we select the candidate, just add it to the ensemble, freeze its weights, and continue with the training. Well, but you may ask, what about overfitting? Because we are just increasing the complexity of our model pretty much in an unbound manner. And the common knowledge from all machine learning courses teaches us that if you just increase the capacity of your model, at one point you will start overfitting. And even though your training accuracy will go up, your test accuracy will plummet. So, please show of hands again. Who ever heard about something called VC dimension? Okay. Which one of you ever thought that this thing could be useful in practice? Very well. It still really isn't. But we will use something different called Radamel Complexity. And what this thing allows us to do is that it allows us to derive something close to a following equation. And what it tells us is that if we have a training error of our classifier, and we know the complexity of the classifier that we can compute thanks to the Radamel complexity, we can upper bound the test error with high probability. Or in other words, this thing can give us upper bound on test error, even though we have never really seen it. What we can use this for is that based on this complexity and training error, we can actually decide whether it's worth it to grow our ensemble with more complex architecture, or we will be prone to overfitting. And this allows us to directly optimize the upper bound on a test error, which is usually quite uncommon, because usually just optimize the training error and maybe look at something like validation. However, in practice, Radamel is much less. It's very tricky to use in practice, mainly because the complexity grows exponentially with the depth of neural network, which makes the bound quite loose very fast, and not that useful for comparing which model to add and which not. Furthermore, it adds another scaling parameter, or hyperparameter, that you need to tune, and that you need to get correctly to make it work right. However, this theory leads us to a very nice claim that ensembles can really generalize better than single tower architectures. And from this theory we can show that yes, there is some theoretical grounding for why using ensembles should be better than using just single big models. Well, that was theory. Let's see whether that actually works in practice. First of all, if we want to compare our method to something, we need to figure out what are our baselines. So, we will try to work with image classification problem, and we will play with two datasets, CFAR10 and CFAR100. These models used to be state-of-the-art in year 2018, which was a long, long time ago for machine learning startups, so please take it with a grain of salt. There were three types of models that we compared ourselves against, and all of them were AutoML based models, or models that were found by architecture search. There is NASNet class of models, or NASNet A, that we already talked about a little, where authors used reinforcement learning to predict the correct block and then just stack that on top of each other. Then there is NowNet, where again, authors used, but not reinforcement learning, but continuous space optimization to arrive to the optimal architecture. And finally, there is AmoebaNet, where authors again used reinforcement learning, but with slightly tweaked reward function for the agent. The main two baselines that we are going to look at is the NASNet A6 and NASNet A7. We'll call this a small NASNet because it's smaller, and big NASNet because it's big. We see that the small NASNet has roughly 10 times less amount of parameters than the big one. And we also see that we are comparing ourselves to something that has more than 100 million parameters. The big NASNet achieved classification error on CFAR10 around 2.4, and on CFAR100, 16.03. So, what is actually our model? Our first question that we would like to answer is that if you look at big NASNet, NASNet 7, it pretty much looks something like this. You just take the cell and stack it on top of each other n times. So you have the width of the model, m, which is the second number, and you have the depth of the model, n, which is the first number. And the question is this really the best way how to allocate this parameter budget? And wouldn't it be better to instead use ensemble of 10 NASNets and have these cells more kind of spread across the model? So we are going to compare the big NASNet 7 versus 10 small NASNet 6. So these are the baselines again. And surprisingly enough, it turns out that we are able to improve the result of the big NASNet while still having roughly the same amount of parameters that it had. So we improved the model by 0.1% of error, even though know that the error bars are quite high. And I guess the only reason why we can say that we improved it is because we couldn't find the error bars for this model. And they would probably overlap, at least a little. But yeah, we see that on CFAR 10 we improved the error. And on CFAR 100, we, surprisingly enough, arrived into the new state of the art. This was quite surprising because all of these models had to be tuned or had to be hyperparameters of all of these models had to be separately tuned on CFAR 100, while our model wasn't at all. And we just used the same parameters that we used for CFAR 10 on CFAR 100. And we were able to beat even a model that had 4 times the amount of parameters. So we called it a bit of a win. But we would like to push this slightly further. And we would like to do some kind of AutoML or something close to it. And the problem is that when we just ensembled, we still had to inject some expert knowledge to the algorithm because we had to decide what architectures are we going to ensemble in the first place. So what we are going to do, we would like to try to let the algorithm actually decide what architectures to use and how to grow them. So what we are going to do, we are going to start with a very small NASNet, NASNet 1 240, which is pretty much the smallest reasonable NASNet that you can start with. And then we will let generator G to propose 2 new different candidates. One of them will be deeper than the previous one, and one of them will be wider. So in one, we will just use more cells stacked on top of each other, and in the second one, we will just increase the number of convolutional kernels, pretty much. How does this perform? So it's here, AdaNet SGD. Again, we have roughly the same number of parameters as the big NASNet. And what we have? First of all, on CFAR 10, we were able to kind of match the performance of the big NASNet, which is still a win because we removed some of the human expert knowledge or human expert bias. And we were actually able to improve the performance on CFAR 100. And even though our dynamic growing was not as strong as ensembling, we removed some of the human expertise, so it's still a quite valid result. But this was interesting that on CFAR 100, we actually improved over the big NASNet baseline. The question was why? Well, it turned out that we can look at this graph. In this graph, each dot represents architecture of one candidate that was selected during the architecture search process. So each dot has its own depth and its own width. The blue ones are on CFAR 100 and the red ones are on CFAR 10. And what we can see is that the algorithm systematically chose very different architectures for these 2 different data sets. On CFAR 100, we have architectures that are very, very shallow, but very wide. While on CFAR 10, we have architectures that are more balanced. And sometimes the algorithm chose to increase the depth, and sometimes it chose to increase the width. This may be a very good reason why we could actually need AutoML. And why? Because normally, if people would try to train something on CFAR 10 and go to CFAR 100, they would just take the exactly same architecture as they knew worked before. However, based on this graph, we can tell that that may not be optimal, and that it may be a very good idea to actually let the algorithm decide on its own based on the dataset. Well, so we have this nice ensembling framework and these nice growing tricks, but we can also try to use some already well-known ensembling tricks, like, for example, knowledge distillation. What does knowledge distillation mean? When we are training the next set of candidates, we already have a bunch of trained networks. So why shouldn't we make use of them? And what we can do is that we are not only training the candidate with the true label and with the classification loss L, but we train it with the classification loss and something called knowledge distillation loss. In this knowledge distillation loss, we are forcing the new candidate to have similar predictions on logits as the candidate previous, and this is the previous candidate. And we hope that this already learned information about class correlation will somehow help the new candidate perform better. We have two types of knowledge distillation. First is born-again knowledge distillation, where we are distilling from the previous candidate. And second is adaptive knowledge distillation, where we are distilling from the whole ensemble that we already have. Second trick that we would like to try is that each time we just took all the candidates, H1, H2, H3, and just ensembled them together, which means that we just took their predictions and averaged them. However, this may not be optimal, and we can try to weight these candidates by different weights W1, W2, W3, and then take the weighted average of these predictions. Nice thing is that we can train these weights with methods like gradient descent or stochastic gradient descent. And actually, if you would like to use the theory, it could turn out that doing it like this have again some nice theoretical guarantees in theory. However, how does it work in practice? Well, on C500, we were kind of able to slightly improve the error, even though the error bars are overlapping quite a lot, and the result is probably not very statistically relevant. And on C500, it actually got much worse. So it may be true that these tricks are not that useful in practice. However, the importance of these tricks is that we implemented all our experiments in the framework called AdaNet, that is open source and public. And implementing these tricks was fairly easy. And maybe someday you will just wonder, I would like to do some knowledge distillation. And with this framework, it's fairly easy to do. So, yeah, the thing about AdaNet is that it started as a very theoretical academic paper, but now it's not just an academic whim, but it's actually a quite well-working service that's used across various Google products. So if you would like to try this, it's one of the black box algorithms that run behind the Google AutoML services, which is a service where you can just send your data, and Google will run some AutoML algorithms to try to predict the values that you would like. It's also used in various other internal Google applications, which I cannot really talk about. But we try to use it for different domains as well, not only for images, but for speech classification. And there is a paper, I think still pending in a submission that should be accepted soon. Text classification, so even you can do such growing and ensembling for recurrent architectures, and for structured data as well. And because the framework is quite easy to extend, it can support funny things like GANs or autoencoders. Well, and even though it contains some fancy theoretical guarantees and a lot of math, it turns out that in practice, a lot of times it's just easy to take a bunch of smaller models and ensemble them together. So, this is all nice, but let's talk about compute and about the promised GPU that I talked about in the title of this presentation. So here are the various architectures that we encountered across this talk. Here are what resources in terms of time and GPUs you need. And here is how many GPU hours it actually is. So if you just want to take a small NASNet and train it to the accuracy that they got in a paper, you will just need to spend 38 GPU hours. If you want big NASNet, however, you will go to 140 GPU hours, which is roughly 5 days. And if you would like to use our ensembling method, you will go to 1.2 thousand GPU hours. So it's not 100x, it's just 10x. So, woohoo. If we add the architecture growing and actually something that could be called AutoML, we again slightly increase the computation requirements to 1,600 GPU hours. Well, that sounds like quite a lot, but keep in mind that this thing is actually doing some AutoML, and these numbers, these first three numbers, were just for training somehow generated architecture. If you would like to run the AutoML part of the AdaNet and really run the reinforcement learning algorithm that came up with the block, you would need roughly 800 GPUs and around a month, which turns out to be pretty much 500,000 GPU hours. Luckily, in the next paper, they improved it to only 50,000 GPU hours. And you may remember that we only talked about CFAR 10 and CFAR 100. So what about ImageNet? The thing is that if you, pretty much this is the problem. If you would like to train this architecture, the AdaNet A7, to the actual state-of-the-art accuracy that is presented in the paper, you would need this amount of resources. So 100 GPUs for pretty much a week, which turns out to be a 20,000 K GPU hours for just one experiment and one run of one number in your paper. Well, and doing architecture growing or ensembling on this thing turns out to be quite problematic, even if you are in Google, or if you are AI resident in Google. Well, that leads us to a question of who wants to be a millionaire, and it is how to get that many GPUs. Well, you have a first option, and you can just go to Alza or Hebreka or whatever is the equivalent here. But because of the cryptocurrency mining boom and all similar things, the price of a GPU that we've been using was around $20,000 when I last checked, which was, I guess, half a year ago, so those prices probably dropped quite heavily. B, you can beg your advisor or your university for a grant and then buy this GPU, which will probably give you like 1/10 of the money that you need and 1/10 of the GPU that you would like to have hundreds of. C, you can go to cloud, but when one GPU hour at cloud costs roughly $1, it will cost you a small fortune just to get one number maybe right. Or D, you can just donate your soul to a big corporation and then use their resources, which is a thing that you may or may not want to do for various reasons. First of all, well, is this concerning? Yeah, kind of a bit is. And there are a lot of people that are starting to worry about how machine learning is being privatized and how only a few people are actually able to publish state-of-the-art results because they need that amount of compute. And it also leads us to a question, well, what will the AutoML mean for various people, and will it mean, I don't know, machine uprising, or are we going to lose all our jobs and we should just go home and do something else? Well, I personally think that AutoML, even though it has some very nice wins and some very nice results, may not always be a way how to best do things. And well, if you cannot afford 100 times the computation, you may sometimes want to use the expert, which turns out to work fairly well for a lot of purposes. Will AutoML take our job? Well, personally, I don't think so. But I think it will add a nice new level of abstraction, a nice new tool that you can play around with. So, for example, if you just want to have a first prototype for your project to work, you can just use AutoML and see what it does, and start from there. However, I actually think that it will help us quite a lot. Because if people that create these AutoML frameworks are forced to create good AutoML libraries that are open source and free to use, it may help us to, for example, implement some weird tricks that were mentioned in the paper, or implement the method that we always wanted to try, but never wanted to implement because it turns out to be quite hard. Well, that kind of sounds like almost you could just now go home and try to use some AutoML and try to use some AdaNet. And it turns out that you can. As I said, AutoML is open source machine learning framework that's currently resided under TensorFlow at AdaNet. And in just a few lines of code, you can import the library, define the problem that you are going to classify, and then define the candidate pool of models, like linear estimator and deep neural network estimator that you would like to automatically ensemble with AdaNet. Then AdaNet will kind of take care of the rest. You will have a nice object called estimator on which you call train with your dataset, and you can evaluate on your data. Nice thing about AdaNet and the AdaNet library is that it allows you to work on different levels of abstraction and complexity. So if you just want simple ensembling, you do this. So if you have your current machine learning model at work or school, you just write it into TF estimator, and voila, you have an ensemble of them. But if you would like to use some of the ideas like growing or knowledge distillation or mixture rates, you can do that, but you will just need to extend a bunch of classes and create the AdaNet object in a slightly different way. Finally, because this project is led by a very good software engineers, the AdaNet library actually is not only an academic one, but also have things like tests. And until recently, it had very decent coverage, but I think now it's migrating to TensorFlow 2.0, and that's causing some troubles. So, as I said, all the experiments that I presented here are open sourced and available under TensorFlow AdaNet. So please feel free to fork me and reproduce my results. It should be runnable out of the box on cloud. So if you have some spare Google Cloud credits, please feel free. And finally, keep in mind that the application process for AI Residency 2020 will start soon. And Jeff will definitely like to see you there. So, thank you very much. That's all for me for the talk.
Thank you very much for the presentation. And now will be the question section, and we should switch to Slido here. Can you please help me?
To někde?
To malo být. Tak, a tady někde prezentovat, to možná to zelené. Čekaj.
Hej, vpravo hore zelené.
Great. So let's go to the questions, and this code you can ask the questions and also upload the one you like. So, is the upper bound on test set really used in AdaNet to stop growing?
No. Or it depends on the application. It turns out that this upper bound is quite hard to get correctly, and because it grows exponentially, it's not always as good in practice as you would like to. For the purpose of our paper, it was never used, but I'm not sure if this is public or if the code for this is public, but you can compute the complexity for pretty much arbitrary architecture, and then for some applications there were cases where the complexity actually helped, and where the complexity was actually a good measure of how well your model will generalize, and when it is good to grow it and when it's good to not grow it. And, and there is some fun research going on how can you replace the complexity with something else. Like, for example, you could replace the complexity with validation set, or you can actually train a machine learning model to predict how well your architecture will generalize, which is quite surprising, but to some extent it works.
So basically it's usually faster to just have a validation set and just validate than to compute the complexity.
Depends on your data. If you don't have enough data, it may be a good idea to either not use the complexity, or if you have to, then use the complexity, but you will have to play with it more.
Okay. Does ensemble smaller AirisSea than tower architecture using the same number of parameters? Maybe does ensemble have smaller Radamel complexity than the tower architecture using the same number of parameters?
Yeah, that's the interesting thing, and that's why we are actually driven to use the ensembles. And it turns out that, yes, the complexity of the ensemble is pretty much the average of the complexities of the parts of the ensemble. So if your candidates in the ensemble are smaller, then the overall complexity of the whole thing is smaller. But even if, the nice thing about this is that if you have one candidate in an ensemble that is small, like very, very small, it can drive the complexity down even if you have something that's potentially overfitting because it's too large there.
No, so is it actually like something that we can already use in our projects? Like if you're overfitting, then add a simple classifier to the ensemble and maybe it will help?
Yeah.
Can I interpret this result?
Yeah.
It's pretty interesting.
Or I hope so, yes. That's how I interpret it as well.
The difference in the depth width of the candidates at CFAR 10 and CFAR 100 has implications for transfer learning. Have you considered to explore this in the future?
Well, it would be very nice to explore that in the future, but as I'm currently not affiliated in Google with anyway, it would make it a bit problematic. But it looks like that the thing is actually slightly more simple that we would like to, and that is that CFAR 10 has only 10 classes, and CFAR 100 has 100 classes. And it looks like that you can use like a rule of thumb, that if your dataset has much more classes, you want architectures that are wider than the ones that have low amount of classes. So maybe the answer is actually much simpler and you don't really need kind of employ AutoML for transfer learning, but maybe you do. Maybe it's hard to tell and it's hard to say how those classes should look like and whether you should really just increase the width of your model. But as a first step, you should definitely try to adjust the width based on the number of classes that your dataset has.
Nice. So actually, if you are trying something like binary classifier, then probably you should use a DeepNet for a baseline. And if you had hundreds of classes, maybe you should use some wide architecture as a baseline for a transfer learning?
Well, I guess, yeah, but probably it's hard to tell. So
yeah.
You just have to try.
And maybe I will just extend the question. There was have Google think about exploring something like this? Like to explore what's good for different transfer learning tasks?
Google is definitely invested in transfer learning, but I really don't know what they are doing there.
Okay, so does this ensembling rocks result hold also for other model types such as boosted forests? Or
I guess boosted forests are kind of by default ensembles, right?
Yeah.
Oh, sorry.
That's true.
So yeah, I guess having an ensemble of boosted forests would mean that you just have a bigger forest. But what looks like it's helping is that you can have combination of trees or forests and neural networks. And AdaNet actually supports that, which is quite nice and surprising.
So the Radamel Complexity result is for neural networks, or is it also like general and doesn't care about the underlying model? Maybe let's rephrase it like this.
I'm not sure, to be honest. I think that the result about the Radamel Complexity is kind of more general because it's like for continuous class of functions. Like VC dimension is for something that... No, sorry. Radamel Complexity is for continuous classes of functions, like neural networks, because you have continuous numbers there. But I think that's the only requirement. So if your classifier is continuous To be honest, I'm not really sure about the definitions, and I guess Wikipedia is just the best source for answer to this.
Okay. So, how did you enjoy AI residency program? What was best? Tell us some good story.
I found my roommate on Reddit. But yeah, the AI residency was very awesome. And definitely the fact that I guess one of the best things was the on-site, or that was the story that kind of synced up with me the most. And that was that you are having a lunch after you had an interview, and then you just like look to the left, and you see a guy in a leather jacket, and you're like, that's strange. Then you look to the left again, and you see like an old guy sitting at the end of a table that seems kind of familiar. So you just like ask the next person, like, is that that guy? And I was like, yes, that's him. And I was like just Hinton sitting there. But from the AI residency, People there were really amazing, and just the feeling of all those people grinding away research and just having singular goal of life for 1 year and just kind of going all out on it was a very nice experience. And overall, the people there were just awesome. Like, there were not some very weird nerds that you could have expected, but they were just like normal crazy people that just went nuts a bit in some things.
Nice. I'm sure that there will be more stories in the networking section.
Yeah,
right?
just hit me with a beer and stories will go.
So, mentioning privatization, is it possible machine learning will soon be driven only by a huge corporation, or is there a light even for some smaller companies?
This is kind of a hard question. How it looks like right now is that in those big corporations that are doing those insanely huge models, there's a lot of people that actually care about academia more than they care about business. So a lot of those models are open sourced, and a lot of those things are actually usable by small startups. So I don't think there is a lot of small companies that have the resources to, I don't know, train BERT model or some large transformer model, but pretty much anybody can use them because they are available online and you can just download them. So it's possible that the privatization of some parts of research is going to happen, but it may not be a bad thing for small startups.
I mean, even if you have the open source project, then it's financially impossible for you to train the model. You know, it's like if they don't release the model, then it will be privatized, even if everything is open source and published. This is probably the bigger question, but yeah, we'll see in the future probably. So, can you use AdaNet with TensorFlow boosted trees for tabular data? Do you think it is a good idea?
Yes, I think it's a good idea, and I think it's actually working. What we were trying to do, actually as one of the first projects that I did, was to use AdaNet on autoencoders. There was a while ago a competition on Kaggle. I'm not sure on which data set it was, to be honest, but the winning solution was based on autoencoders, and they used a very dirty trick where they trained the autoencoders with their training and test data as well. It was kind of valid because they have not used the labels of the test data, and then they just trained some classifier on top of that. And the result was actually an ensemble of such autoencoders and classifiers. So you can use that for tabular data, and it looks like that if you would add the boosted trees to the mix of the ensemble, it could help. Jeez.
Sorry for the technical difficulties. If somebody has a question from the audience and doesn't have access to internet or something and cannot, just raise your hand. We can ask question also directly. Okay, so is there a comparison of Google's AutoML versus AutoKeras versus H2O's AutoML?
I don't think so right now.
It's pretty much new, yeah, so.
Sorry?
It's very new.
Yeah, I guess it's pretty much new. I think that the author of the AutoML, the AdaNet, oh sorry. Yeah, I really don't know what are the comparisons and which one of them would work the best and which one is the worst. I'm not sure if even Google has internal ones, and if they do, I don't know. But I would encourage you to do such a comparison and write a blog about that. It would be definitely a very useful one.
Or maybe publish a paper.
Yeah, exactly.
What areas of machine learning you think will bring most interesting breakthroughs in near future?
Well, this is a kind of nasty thing to do, because as it turns out, predicting future for especially technology is usually a suicide for the speaker. But I don't know. I think that just figuring out the correct applications of machine learning for applications in real life is the one that is going to have the most impact. And it's not necessarily about whether you are using, I don't know. Sorry, if you are asking about academic impact and what will be like the most hyped paper in next year, I have really no idea. And it's probably kind of hard to tell. But if you're asking about practical implications, I think just finding interesting applications in the real life. I guess that's kind of it.
So it's not about research of the like exotic architectures, but just you find the usage of machine learning that will help a lot of people.
I guess, yeah. And yeah, like everybody is waiting for capsule nets, so you know, who knows?
Is there some new paper on capsule nets besides the original one? I don't think so, right? So would it be possible to use pre-trained submodels and therefore reduce the learning requirements for ensembles?
Yes. And actually one of the modes of how you can grow the ensemble and how you can grow the architecture is that you can not only propose the bigger and smaller candidate, but you can also propose a candidate with the same architecture as the previous one. And there you can use some tricks like periodic learning rate schedules. So for example, there was a paper on, I think it was actually the Born Again Networks paper, where they just trained one model, but they didn't have like a decaying learning rate, but they had kind of saw-like learning rate. So the learning rate was decreasing, then it increased, decreasing, increased, decreased, increased. And this produced a surprising variety of models that they were able to ensemble and get better results. So pre-training definitely helps. But the problem is that pre-training models with different architectures is kind of hard to do if you don't really know what the architecture will be selected by the algorithm.
But that's a pretty neat idea. I mean, if you pre-train the building blocks on like a lot of like different tasks and then just use the algorithm to select the pre-trained one and combine it in an ensemble way, that will speed up and maybe get better transfer learning results. That's a pretty neat idea. And the last question, opinion on weight agnostic neural networks from Google Brain by Hardmaru. Do you have some idea?
I'm sorry, but I'm not really familiar with that.
Maybe the asker would like to
clarify
and bring more details in the questions.
Or maybe during the networking part.
Maybe during the
networking. I was bit out during the last few months on a very intensive vacation.
Okay, so thank you very much for the question session. And I would like to thank all of you to attend this meetup. And I would also like to thank our partners that will be displayed soon. And it's Impact Hub as a venue partner for providing us this space. And then some awesome companies that do machine learning such as Rosum, Seznam.cz, Konica Minolta, or CEAI. And I would like to I would like to invite you to the next meetup, which will be in 1 month, 24th of October, which will be about machine learning in limited medical data sets by Jiří Mekiska from Faculty of Electrotechnics, and he's specializing in working with really small data sets, helping cure some exotic diseases. And I would like to also call on the stage the whole organizers team of the machine learning meetups. Come on, guys! It's a work of a lot of people that are helping. So please applause for the guys that organizes this. And in the back there will be some refreshments, some food, some beers. So enjoy, network, talk to each other, and talk to the speaker, talk to us about everything that interests you. Thank you.